In this final lecture of Lesson 3, I would like to talk about arguably the most important theorem of measure theoretic dynamics, namely the Ergodic Theorem. So what is the Ergodic Theorem about? As usual, we start with a probability space and a transformation of the space that preserves the measure. So we have seen in the homework that there is a strong recurrence property that's called the Poincaré recurrence theorem, namely that for every measurable set E in the space X that has positive measure, almost every point in that set returns to E actually infinitely often. Now this is a qualitative statement, right? Because it just says, well, there is a quality of recurrence in every measure theoretic dynamical system, right? But we could phrase this question a little more quantitatively. Namely, can we say something about how often a point returns to this set on average, right? So if we have a certain time, t, can we say up to time t, how often on average do we return to E? And to make this a little bit more precise, let's look at a concrete example. So assume our space is just a sequence space over a finite alphabet, and T is the shift mapping, and E is a cylinder set, right? So assume that it has positive measure, and we have a measure that is invariant under the shift mapping. So what does it mean that a sequence X returns to this set under the shift? Well, it just means that sigma occurs as a substring in X, right? Because for X, or for an infinite sequence to be in this set here, just means that it starts with sigma. So X starts with sigma. So for X to enter E after some finite amount of shifts just means that at some point sigma occurs in here, right? So we would have sigma, and then iterating the shift map, right, would just mean that this sigma gets shifted towards the front, and then eventually X enters E. So entering or returning to E just means that at some point sigma occurs as a substring in X again. Then the average number of returns to sigma by time n is given as this quantity here. So the cardinality of the number of all i's less than n, such that sigma is a substring of X starting at I, and then divided by all possible positions between 0 and n, namely n. Now, of course, we can ask, does this average converge, right? And moreover, we would think if this transformation is well behaved with respect to the measure, how often should a substring occur? Well, it should somehow be related to how much measure is put on this cylinder set sigma. So in the easiest case, think of sigma just being a cylinder defined by a single bit, something like sigma, 0, right? That would mean how often does 0 occur in the sequence? Well, that should somehow be related to the probability that 0 occurs, namely the measure of that cylinder set. So mu of cylinder 0, right? Right, and that is precisely the statement of the Ergodic theorem. It's the subject of the Ergodic theorem, which we will turn to now. The complete statement of the Ergodic theorem is a little bit long, so we kind of take it one statement at a time. As usual, we start with a measure-preserving transformation on a probability space. So the first statement concerns precisely the averages we mentioned or looked at the previous slide. So if f is integrable with respect to the measure, right? Then the average, right, of f of t to the ix, right? So we evaluate x, and then the images of x, the first n images of x under t, under the shift, right? And this is where we evaluate f, right? And then we average these values out by n. And the ergodic theorem says that this converges to some value for mu almost every x. So what we essentially do is we follow the orbit of x, evaluate f along this orbit, and then take the average of all these values, right? And the ergodic theorem says that this average actually converges for almost every x. So let's define the limit function, right, by f star. So let's say this limit here, which is defined for almost every x. So f star is defined for almost every x. Then f star is integrable, so it's an L1 function. And these L1 functions are, they need to be defined only up to a set of measure 0, right, which comes out of here. And for this function, it holds that the integral of f star is the same as the integral of our original function f. And furthermore, f star is t invariant, which means that f star composite t is the same as f star. So that's the second part of the ergodic theorem. So that just says that, well, the first part says the average exists almost everywhere. It defines a function that is well behaved in the sense that it's integrable. It has the same integral as the original function, and it has this nice feature that it's invariant under the mapping T. Now the third part says that if our mapping is actually ergodic, so remember that meant if you have a T invariant set, right, that is measurable, then it has to have either measure 0 or measure 1. Well, if our underlying system or mapping is indecomposable measure-wise, then our f star is actually a constant function almost everywhere, right? And that means the value, so the constant almost everywhere value of that function as f star must be the integral of f, right? Because if you integrate a constant function over a probability measure, right, you just get the constant value, right? But this integral must be the integral of f, so the value, the constant value of that function f star must be the integral of f. And now, since f star is the limit function, that means that for almost every mu, almost every x, this average here converges to the integral of f. So you can think of this as follows. Well, an integral, right, is something like a continuous average of a function, right? Whereas here, we're taking finite averages, but more and more of them, right? Now this says we're averaging out f at a certain a number of points, and these points are given by the orbit of x under the mapping T. So now the ergodic theorem says in this case, if the underlying mapping is ergodic, then this averaging, so this sampling of the function at these points here is so good that it eventually will be as good in the limit as averaging the function over the whole space continuously, right? Let's do an example. Namely, we can see the ergodic theorem as a strong generalization or far-reaching generalization of the law of large numbers. So let's start with a binary Bernoulli process, right? So each of these xn's is a binary random variable with probability, so identically and independently distributed, with probability for 1 is p and probability for 0 is 1 minus p. Then let mu p be the Kolmogorov measure of this process on the sequence space, the binary sequence space. So that means that the 1 cylinder gets measure p, the 0 cylinder gets measure 1 minus p, and mu p is invariant under the shift map. So now we say f is the characteristic function of the 1 cylinder. That means f of tix is 1 if and only if tix is in the cylinder 1, and we saw on the first slide that just means that the ith bit of x is 1, right? Because again, if the ith bit of x is 1, right? If there's a 1 here, then that means in I steps we actually shift this through all the way to the start, which then means that here we actually are in the 1 cylinder. Now, the ergodic theorem for this special setup here says the following. For mu p, almost every x, right? We know that this is, we've seen that this is an ergodic mapping, so the shift is ergodic. So we know that this limit here exists, but what is this now? So this is f of tix. Well, this is just the number of positions, number of bits less than n that are equal to 1, right? Divided by n. And now we take the limit of this, right? So another way to write this is just, since we have either 0 or 1, we can just take the sum of x0, x1, and so up to xn minus 1 over n, and take the limit of this. By the ergodic theorem, right, we know that this must converge to the integral, right, of, so this must converge to the integral of the function chi of 1 d mu p, right? But the integral of a characteristic function of a set is just the measure of a set. So mu p of 1, which I already wrote here, 2, right? So that must be the limit, but that is just p, right? This is just p, which is exactly the law of large numbers, the strong law of large numbers. Almost, for such a process here, almost every sequence has a limiting frequency of 1s, that is the probability of 1. So in this sense, the ergodic theorem can be seen as an extension of the strong law of large numbers to arbitrary stationary processes. I would like to say at least a little bit about the proof of the ergodic theorem. So first I want to go over kind of the high road, take the high road and do an elegant, or indicate at least how to elegantly prove this theorem. And then I want to go a little bit more into details and present a more combinatorial hands-on approach. So first of all, let's just consider a real valued function. So theoretically we have to consider complex valued function, because those are the L1 spaces. But of course you can split it up into real and imaginary part and then consider those separately. Okay, so we want to show that some limit, this average, the limit of these averages exists. So what we do is we split those up, right? So we consider the lim sup of those averages, and we consider f sub star is the lim inf of these averages, right? And of course we would like to show that they agree. So the lim sup and the lim inf agree mu almost everywhere. Now if we have two real numbers r less than s, we can consider the set E sub rs to be the set of all x in our space for which the lim inf of these averages is less than r and the lim sup is greater than s. So you can think of this set ERS as collecting the bad x, right, for which the lim inf and the lim sup actually differ. So you can think of this is R and this is S, and then our averages sometimes or infinitely often actually dips below R, and then it goes up over S and then crosses down below R, and then it crosses about F, but it may cross up to S several times before it dips down below R again. Anyway, but we have infinitely many of what is called these upcrossings here, namely from below R to above S, right, that have to happen. And what we would like to show is that the measure, so this here is actually a very small set of measure 0. We can make our life a little bit easier by noting that this set here, where the lim inf and the lim sup differ, can actually be written, since if they differ, they have to differ by some amount, and since the rationals are dense in the reals, we can write this set here, so the set that collects all bad x, as a union, a countable union of these sets ERS. So what we need then to show is that this set E sub RS for any combination of RS has measure 0. The way this is now usually shown, namely that these sets the sets E sub RS have mu measure 0, is as follows. You try to bound the integral of f over ERS d mu from below and from above. So you bound it from below by, well, of course, so a standard way to bound an integral is to take the measure and take a lower bound of the function on that set over which you're integrating. Right, so if in the most simple example would be if you have a function and let's say you want to integrate over this set here, right? We have a lower bound here, right? Then it would be just the measure of the set. So let's assume this would be ERS, and then this would be our S here, right? And then we would have S times the measure of this set, right? Now, that's not quite the case here, right? Because we don't have actually a lower bound on f in the form of s. We only know that the average of f along the points in ERS infinitely often jumps over s, right? So it's a little bit different statement, different situation. So one has to work a bit to show this, right? But a similar idea then works down here, right? So here we also know that the values, right, of the averages of f along the orbit of our point in ERS, our x in ERS, infinitely often jumps below r. Right? So then the idea is that we try to turn this into an upper bound on the integral, r times this, right? And if indeed r is less than s, then this, of course, right, since we have identical quantities on this side, this would of course force, so then this can only be true that this is greater than or equal to this. This can only be true if the measure of E sub RS is 0. And that these inequalities indeed hold follows from a different ergodic theorem. So the one that we saw before is also called, is only one of many ergodic theorems that are known by now. It's arguably the most famous one, and it's often called the theorem is called the pointwise ergodic theorem, whereas what we need to prove the pointwise ergodic theorem is what is called the maximal ergodic theorem. What does the maximal ergodic theorem say? Well, again, we start with a measure-preserving transformation on a probability space and an L1 integrable function. Now we define f star, our lim sup, as before. Then you can show that for any lambda, any real number lambda, if we integrate f over the set where f star pointwise is greater than lambda, right, then this is bounded precisely by lambda times the measure of f star greater than lambda. Right? So this is just a different way, a general version of the first inequality we had on the previous slide. Right? If you go back and compare those two. I should say at this point that this is already kind of almost a special case of the maximal ergodic theorem that is tailored to our situation here. If you go into the literature and the book on ergodic theorem, then you will find a statement of the maximal ergodic theorem that is much more general and looks much more general than this. But this captures perfectly the spirit of this theorem. So I'm not going to give a proof of the maximal ergodic theorem. It's actually not very long. You can prove this almost in half a page. And if you go to a standard textbook, modern textbook on ergodic theory, you'll find a proof there. It's not very hard. And instead, what I want to do is get a little bit more hands-on, because I feel that this maximal ergodic theorem doesn't really give you a good idea of why this is true. And instead, I want to try to give a more direct proof for the ergodic theorem in a special case, namely that t is the shift on 2 to the n, and mu is shift invariant and ergodic. Right, so it's a special situation, but fairly captures fairly good what the situation we are interested in. Okay, so let's try to give a more direct proof of this case that we had in the example, namely that in this case, the average occurrence of the number of ones must converge to mu of 1. And note we don't even assume here that our mu is coming from a process that is IID. It's just shift invariant and ergodic, right? So it can be a different measure as well. We just want to show that the number of ones asymptotically, so the frequency of ones asymptotically goes to the measure of 1. So suppose the statement is false, right? So that this is not true. Well, then either the lim sup is too large or the lim inf is too small. Right? It does not converge there. So let's just assume without loss of generality that it's the lim sup. And then we know that for some epsilon, right, this set here, the set of all x, sequences x, such that the lim sup exceeds the measure of 1 by epsilon, right, is large. That means it has positive measure. So we want to show, we want to derive a contradiction from this, right, which then would mean that this actually must have measure 0, as has the corresponding set for lim infs. So first we note that E is T invariant, right? So if I take T of E, that's contained in E. So if I shift everything by one position, that will not affect this lim sup here. It will not affect asymptotically the number relative frequency of ones, right? So we have this, but then since we assume that our measure of transformation is ergodic, we know that this set then, since we assume it has positive measure, well, by ergodicity, it must then actually have full measure. So what does that mean? almost every x is in infinite sequence x has a long stretch of too many ones infinitely often, right? So because it means the lim sup is greater than mu of 1 plus epsilon. That means, well, to have this property for a lim sup, it must mean that the frequency of ones up to n infinitely often must be greater than this value here. So infinitely often I have sufficiently long stretches that drive this value above this threshold here, right? So that's what is meant by this statement here. But this is contrasted by something that directly seems to contradict this. Namely, on the other hand, at any finite point in time, so if I just take averages up to a certain point, fixed point in time, let's say n, right, the expected value of this number, namely the frequencies of 1, must be mu of 1 because of this identity. So mu of 1 is just integrating the characteristic function of the cylinder set 1 over the measure d mu. But t is measure preserving, which means we can insert it into our integral in this form. So this integral is the same as this integral. That was one of the properties of being measure preserving. And we can actually do this a number of times, iterate this, and take averages, right, and get that this is still the same here, right? And now this is just right, as we saw before, is just counting the number of ones among the first n positions and dividing by n, right? So the expected value of this, right, because t is measure preserving, right, all these transformations are possible because t is measure preserving, is the expected value of this is the measure of 1. So what do we have? On the one hand, at any finite point of time, right, so the expected value of the number of the relative number of ones must be the measure. On the other hand, we just assumed that almost every x infinitely often, right, has long runs or an excess of ones, right, that make this average here greater than the measure. So there seems to be some discrepancy or some contradiction there. And that's exactly how we will try to derive a contradiction from the whole thing, from our assumption. Namely, we will try to find a sufficiently long interval, right, that contains many short intervals in which the number of ones is too large for this to hold, right? So what we're looking for is one long interval, right, so capital N, such that many or most of our x's, right, which we know have many intervals of, eventually many intervals of an excess of too many ones, right? So we will try to find this time n such that by that time most of our x's, most of our sequences will have many intervals in which we have an excess of ones. So too many ones in here, too many ones in here, too many ones in here, right? Maybe not everywhere, but on most places we have intervals of too many ones, right? And this composition is possible for most of the x's, not almost all of them, but most of them. And then we use this to actually contradict this averaging property that we just derived here. So let's construct such a long interval. So we start with any sequence in E. So E, remember, was the set of those x's which violate the average in of measure in the lim soup. And we saw that this is invariant under T, so T of E is contained in E. And since this is true, right, so it doesn't, for the asymptotic count of asymptotically, it doesn't matter where you start counting the ones. So for every n then, there must be a minimal s of n. Of course, this function depends on x, so I will often write also s sub x of n, for which this is true, namely xn plus 1 plus so on. So the number of ones in this interval between n and s of n, right, relative to the length of this interval, exceeds the measure of 1 by epsilon. So again, that's true because E is T invariant, right? So if we start counting from n on, it must still be an element of E. So at some, there must be a point, a first point, where we actually see this, that we have this axis, epsilon axis of 1. Now, given x, we can look at the corresponding point where we first encounter this excessive measure, right? That would be Sx of 0, right? So, and only a certain fraction of those x has this, or a smaller and smaller fraction of these x's has a larger and larger Sx of 0. So this first point where we have this violation of this excess of measure. Right? And formally, given a delta greater than 0, arbitrary delta greater than 0, there exists a length L such that the measure of the set of all sequences where the first time we encounter the violation takes place after L is at, so the measure of this set is at most delta square. So if we give up a little bit of measure, namely delta square, we can actually work with sequences that obtain an epsilon excess of ones by a fixed time L. Right? So those are the sequences we'll work with now, namely those that for the first time have an epsilon excessive measure by time L or earlier. Furthermore, not many orbits will visit D very often. So recall D was the set of all x that have reached the excessive measure after time L. So why is that true? So let Gn of x be the average number of visits of the orbit of x to this set D here by time n. So formally Gn of x, average number of visits, so characteristic function of D, visits to this set by time n, capital N. Okay, now T measure preserving implies that the expected value of Gn is at most D square. So this calculation is similar to the one we did before for the expected value of the averages up to a finite time. So the reason here, this here, was exactly the measure of, or was an upper bound on the measure of D, right? And Gn just counts average visits to D by a finite time. So the calculation is the same as before. So you should probably go back and just look at that and make sure that the same calculation applies here. So now we can use Markov's inequality to get a lower bound on the measure of the set Gn, where Gn is the set of all points that visit our set D rather rarely, namely that on average the number of average visit is at most delta. So recall what does Markov's inequality say? So in ours, adapted to our situation here, it says that the measure of all x such that Gn is bounded by delta is bounded from below by 1 minus the integral of Gn d mu divided by delta. So now this here is at most, right? We know that this is at most delta squared. So it follows that we can bound this from below by 1 minus delta. So to sum up, a rather large fraction of points or sequences x, I mean those in Gn, right, with rather large measure, visits this set D, right, on in which the first point where we have an excess of ones happens rather late, right, visits this set rather rarely, right? I mean, relatively or at delta often. So if we put everything together now, and you should probably work out the details, all these facts we had before, we can conclude from that if we have an x in Gn, so an x in the good set, so to say, up to time n, the portion of long intervals, right? So with so long intervals in the sense of we have to wait long to for our first for the excess to appear, right? With starting point in 0 up to n minus 1, so there's an interval of integers here, is not more than delta. So we count the number of points, right, in that interval here, such that the waiting time, right, between n and the point when the measure axis appears is more than L. So that's what I mean by long interval. So the fraction of this relative to n is not more than delta. So that follows from the quite easily from the observations we had on the previous slide. So you should probably sit down and work out those details that this is indeed true. So what we have now is for every number between 0 and n, right, we have an interval, right? So here we have 0 up to s of 0. And then we have 1 up to s of 1. And then we have 2 up to, and once in a while we have a very long wait, right, where we need to wait for a long time to get excess of measure. But for most, but that's only a tiny fraction, namely at most a delta fraction. So most intervals we have a rather short waiting time, 3, s of 3, and so on. Right? And from this property that we just observed, so that there are rather few, at most delta many, long intervals in there, we can now infer a combinatorial fact. It's a purely combinatorial fact to which we have reduced our whole measure theoretic problem now. It's just a combinatorial question or problem for intervals. Right? So from this property, that there are relatively few long intervals now, we can do the following. This is called the packing lemma. And the lemma says that if we have such a good sequence with relatively few long intervals, we can find a sequence n1, n2, n3 up to nk of natural numbers, such that, first of all, the intervals ni up to sxni are disjoint. Right? They are all sub-intervals of the long interval, the big interval 0 up to n minus 1. And together, they cover a rather large portion of this interval, namely 1 minus 2 delta of this portion of this whole of the length of the total interval. So this means we can find, right, so we have our long big interval 0 up to n minus 1, right, of length n. And now we remember we had those small intervals from 0 up to S0 and so on, right? Sometimes there's a few longer among them, but most of them are short. Now what we can do is we can take these some of these intervals here, right? Let's say this one, and so on, right? And build a disjoint family of them, right? So let's say we take the 0 interval, and then some interval further down here, right? And then somewhere lies here, and here, and here, so that together they cover, they're all disjoint, but together they cover a rather large portion of the overall big interval, right? So what does this give us? Well, it gives us exactly what we want, because we know that in each of these intervals we have an excess of 1s, right? So that means, and since they cover a rather large portion of the overall interval, that means that somehow in this large interval then we also must have a certain excess of 1s, right? And now we can use this to get a bound on the number of 1s in the overall interval here. So let's do this, right? So we want to bound the number of 1s in the big interval from 0 to n minus 1. Well, that's just bounded from below by the number of 1s in all the small intervals together. So small interval ni to Sni, right? And we do this for all the k subintervals we selected via the packing lemma, right? Each of these intervals has an epsilon excess of 1s in there, right? Relative to the measure of 1, right? And since we're covering with this 1 minus 2 delta portion of the long interval or the large interval n, right? So here's our lower bound. But now notice that this bound here is independent of x, right? There's no x that appears here. The sequence of these ni's, this can very well depend on x. But no matter then how I choose this, I always get the same lower bound, right? As long as my x is in Gn. But this now allows us to bound the integral, right? Because we have a bound on the on this individual sum here for specific x, right? That is independent of x, so we can bound the expected value of this sum, right? By assuming that x is in Gn, so we have this bound just now multiplied by the measure of Gn. Right, so by just assuming that x is Gn and discarding all the other x's for which this might not be satisfy this lower bound here, so then we just multiply everything by measure of Gn. But the measure of Gn was bounded from below by 1 minus delta. So this here was 1 minus delta, right? And we saw that this sum here before, we evaluated this as, if we average out this sum by 1 over n, we get mu of 1. So if we average out this here by 1 over n, right, then we cancel out the n over here, right? So then mu of 1 is equal to this integral of this sum here, averaged out by n. Right, this n here disappears, so we have a lower bound by the mu of 1 plus epsilon, the lower bound on the measure of gn, times this factor 1 minus 2 delta, right, which we carry over from here. But now let's just spend a moment looking at this. Here we have mu of 1, here we have mu of 1 plus epsilon. Right, so, and there's a greater than or equal to here, to that here. So here we kind of make this expression a little bit smaller by here 1 minus delta and here 1 minus 2 delta. But delta can be chosen arbitrarily small, and it must hold for every delta. So if we make delta very, very small, then we obtain a contradiction, because here epsilon is fixed, epsilon was given. Right, so we make delta very small compared to epsilon, and then we can violate this inequality here. So we have a contradiction. Okay, so that was a little bit of an overview how you can kind of, in a hands-on approach, reduce the proof of the ergodic theorem in this special case to a purely combinatorial fact, namely the packing lemma. You can then actually extend or generalize this approach to the full ergodic theorem, and if you want to read more about it, you can find it in the book by Shields, from which this approach is taken. The name of the book is The Ergodic Theory of Discrete Sample Paths.